Welcome to the next video in the systems programming video series. Picking up where we left off, we have now fully implemented malloc or malloc 2, and we'll move on to implementing free. Free should be considerably easier because effectively all you do is simply go to the address in memory that you are told to free, and so long as it is there, then you set its parameter to 1, saying that it is free. Let's do some fairly standard and tedious checking, though. What if you are passed in memory that doesn't exist, like null? Well, then you just don't do anything, okay? When you are told to free something, right, the user has their own address to the memory, not to the header. So when you do actually receive this memory, you do need to decrement its address by the size of a struct chunk pointer. So let's do that. So let's say that struct chunk, and in particular, the hunk of data that we are talking about here should be struct chunk star, right? We want to cast memory to the type of a chunk pointer, but not only that, but move it back by 1, which, right, you want to do the cast first and then decrement by 1 so that it decrements by the size of something of type struct chunk star. So now it should be pointing to the header data, and we want to check that the memory is not already free. So what if this is already free? Then let's just print a message. So a little bit corny, but don't free the free data. And then I guess what do we want to return? And by the way, this doesn't return anything. So we could just say return full stop. But if it is not already free, then we set it to be free and return nothing, which it already is doing, so we don't have any more to do. So that's free. And as before, I might want to actually call it free2, and I might want to put it in my header so that I can be sure that I am really testing my version of these things. And so that, I guess that would be a void star memory, we'll call it, just like they did. And so there's my stuff. Now, it'll be very interesting to come over to print. And this time, what I might want to do is rather than simply do 2 calls to malloc, I might want to free the pointer x, right? So that's already the address. And what would be nice to see if I printed before doing the free, so cut that out, paste that in. So I should see the number, right, the value 1 and the address of x. I free it, I malloc a new int. If things are set up correctly, then when I malloc this, it will take the freed up space and reuse it, right? It should go search for the most recently freed space and use it up again. So this should be 2, but when it prints here, this address should be the same as whatever that address is, if things are working correctly, and let's hope that it is. So let's see what happens if I call make print. I wonder if that would work now, and it seems to. And then I call print. Ooh. So the stuff for X seems to work. Oh, one thing though is I should call that free too. I wonder if that was the whole issue. That was the whole issue. And look at that, it's working beautifully because the 2 addresses are exactly the same. So it reused the space that got freed. And we already know from our previous implementation that it didn't do that when we didn't free it. So man, I'm happy about that. That is looking exactly like you would hope that it would look. So I guess since this is a pretty short video, we wouldn't want to end it already. And so what do we want to do from here? Well, I guess maybe we have this now implemented. So what comes next? So where did you run your test, laptop or I think that Golden Gate is like their, at Bryn Mawr, maybe that's their university system. But anyway, okay, so I'm running it on my quite old desktop. What are the performance specs of the machine, number of processors, size of RAM? I don't know, am I going to be interested in that? But in any case, allocate, let's just see what's done here. In this question, you will analyze the allocations made by malloc. So simple, write a program, print C. So here I'm actually going to put in print C what it was supposed to have, because I've just been using it because I didn't want to like a new script, which is maybe kind of dumb, but whatever. So so now we're actually going to call sbrk and then print the initial top of the heap, call sbrk again, and print the new top of the heap along with the increase in the bytes, not k bytes. Okay, so I guess it should look something like this. So let's come over to print, call sbrk. So let's say that what sbrk returns an address untyped, you would think, pretty sure. And so let's just say first, and that's going to be sbrk called on 0. And I guess I want to print that. So the initial top of the heap is, so print F, and at this point I maybe want to get rid of that. And what do I put here? Right, the first is %p, I guess, right? And I'll line break and give it first. Then I want to first, well, I guess, let's just say ptr, because I want to be as conservative as possible about this. So let's say p, and then p is equal to sbrk at 0, and printf sbrk. The second is %p. Oh, but I probably want them to be different. So let's say void star q, and so this will be q, and then I want to, what was the other thing? I want to print the difference, basically. So let's see how different they are. Printf, so this is going to be, I guess, just a %d, and this is going to be a %x. Number of bytes in both cases, and so the first one. Now I know that in GCC, although it's a little bit on the weird side, you can cast these to ints, can't you? So if I cast to int p and minus cast to int q, although I want it the other way around because I wanted to take big minus small, and I might even need parens to make sure that it knows what I mean by some of that. And then I want to do what? And then I guess put the same thing. Let's just move it up here. So int x is this, and x and x, so that it prints as a decimal and a hex. So let's save that, make, doesn't like something. Right, from pointer to integer of different size. So maybe I need a long, actually. Right, let's cast this to long. What if I just did that right there? Right, and then if you print a long, then you must do it. Oh, what's the best way to do this? Long, LD, long decimal. Looks like it's also going to not like that LX, maybe. Try that. Oh, right, and these also need to get cast to long. Seems to work. Ooh, that's not good. Oh, funny. Because the point of the exercise was to see the difference, but this actually works almost, you would have thought that it would work, which is that, you would get the top of the heap, which would be some address, especially if you've not used anything yet, then there shouldn't, right? Like just some address. Who knows why it's that address? That's some like a predict, feature of your computer. But the point that was, trying to illustrate here was that if you called it and then called print and then call it again and call print, that they should look different. And then the challenge was to explain why they look different. Did I do this the way it was intended? Call sbrk at 0, print the initial top of the heap, call sbrk at 0 again, print the new top of the heap along with the increase in bytes. Well, man, I seem to have done that, but it doesn't seem to register that I did that. Hmm, like nothing to explain here. What I think the point of the exercise was that by calling on print, the call to print actually performs calls to have access to more heap space without you, right? I think that was part of the point of the exercise was to see this mysterious difference in the two and realize that the explanation was that the call to print itself causes additional heap space requests. But why is it not doing that, right? Why are we not getting that unexpected behavior? Oh, maybe that's because no, that seems right. I'm printing P itself, which is the address, and that's exactly how it looks down here. And I'm calling Q, which is also the address, and that's exactly how it looks here. I did it after calling print, so you would think that the call to print would have changed the top of the heap. Did I not save it? Maybe that had something to do with it? No. So yeah, I'm tried, editing this to see if that, but that just obviously shouldn't be the issue anyway, because these two addresses, you can just look right at them and tell that they're exactly the same. And what's especially mysterious to me about this is that just like a week ago, I did this for the first time, and the two addresses came out different. And when I printed them out, there was some big size difference. So, like, the result is just not the result that I got from doing almost exactly the same thing like a week ago. So, I am really sort of why it is no longer doing what it used to do. And I thought the explanation was that this printf was here, but since it's here and it's no longer showing different addresses, right? And this is printf. I'm in assignment 8. Man, I almost wonder if I should but it's printing what I'm telling it to print, so it can't be that like compiling and running the wrong file or something like that. Kind of, if it maybe because I didn't do this, I didn't have like renamed functions like this and this. You wouldn't think, it doesn't even seem like it's using these things. So why would that make any difference? But let's get rid of that. Let's delete the header file. Let's, I guess, clean and run. I'm just gonna, what if I make? Okay, seems to work. What if I print? Now they're different. Oh, well, I wonder if maybe there was like some of the old legacy things, and this can go away too at this point. But I wonder if like it's like some of the old left around code was getting like over because like wasn't recompiling or anyway. But in any case, finally we see this right here, which actually might be the exact amount that the exercise says. Yeah, 1040 or 410. Okay, well, close. And I wonder, right, that's such a small difference that I wonder if that's just some very small and insignificant difference in how things were implemented in certain places. But in any case, so right, so why is it increased by this much? So my answer now is that this was the old top of the heap address at the very beginning of the execution to main. Print caused it to request more space. I don't know why exactly this, except it might have something to do with like the number of characters, might have something to do with paging, which we did not talk about, and I'm not sure if we're going to talk about. But in any case, this print call is requesting extra space of about this size roughly. And yes, I guess not sure if there's much more to say about that. Okay, finally got it to do what it's supposed to do, so the end.